So, last class we have discussed that if you have a given a functional j is equal j dot is equal to t 0 to t f and v of t x, v is a function of t and x t and x dot at t, and if you consider the one point is fixed and other point is free, then in order to have our job is to find a trajectory, optimal trajectory x t such that this functional is has its extremal values, either minimum or maximum. So, the necessary condition we have derived is this one. So, the first condition is the Euler's Lagrange equation. This equation is Euler's Lagrangian equation. So, you have to solve this one. In order to solve this one, there are two conditions, boundary conditions are there. This condition when T f is free, when T f is free, then you have to use this equation, and x f is x T f is fixed, then out of this one only this is you have to use it. When x T f is free, but T f is fixed, then you have to use in addition to the Euler's Lagrangian this equation. When both are free, that means x T f is free and T f is free, then we have to solve Euler's equation in addition to the two boundary conditions, and these two boundary condition is called the transversality condition. Agree that we have seen it, and we have considered the different cases. If you recollect, we have considered the different cases, case A, B and C, different cases, and correspondingly Euler's Lagrangian equation you have to solve it and the corresponding boundary condition. Further, we have considered the next is we have considered the case 4 when the end point is restricted on a curve, which is a function of t. Agree this, and in this equation that you will get a what is called transversality condition. One is that x dot of t instead of x dot of t minus g dot of t at t is equal to t f. This equation you have to solve. So, this is we have to now after solving this equation, that will get the trajectory, whether this trajectory is what is called optimal, this trajectory will maximize or minimize this functional or not, that we have to check it by using the what is called sufficient condition. We will now discuss that sufficient condition for the functional j is to be optimized. What is the sufficient condition for the functional j will be optimized, mean either maximize or mean minimum value of the function. So, our sufficient condition it is same as what we discuss in case of what is called the static optimization problem for multivariable optimization problems. The same condition will consider here also, sufficient condition. The sufficient condition will give you whether the functional is maximum or along the trajectory, if you use in the functional, that whether it will be maximum or minimum value of the functional, that will give you you will get it from sufficient conditions. So, if you see this our second variation of the incremental what is called functional, that we have denoted by del j square, and that is equal to, if you see the Taylor series expansion of what we have discussed earlier, that means that incremental functional value, the second we will consider up to second derivative of the Taylor series expansion, and that second derivative we will consider now as a what is called the second variation of the functional, that is equal to integration of this t 0 to t f, agree, then del x of t, that whole transpose del square v dot del x square of t. This is a matrix, because we are finding the gradient of v with respect to x, again we are differentiate with respect to x. So, this is the matrix. So, that matrix multiplied by delta x of t vector. So, this and second term, the second term is twice delta x of t whole transpose, then delta square v differentiate gradient of v with respect to x, then x dot or reverse order x dot, this you calculate along the trajectory of this gradient multiplied by delta x dot of t, then plus delta x dot of t, delta x of d, delta x of dot of t transpose delta x dot of t transpose this delta square v dot delta dot square of t, this compute at the, this is the matrix compute at along the trajectory, star means along the trajectory delta x dot of t, that this bracket and this bracket is complete, this and this complete, and then differentiate with respect to t. So, this quantity inside the bracket of this one is a scalar quantity. So, we can write it in terms of quadratic form, that you know quadratic form is nothing but a x transpose p x form, we can write it. So, how we are writing this one, you just see this one, this integration of t 0 to t f, then we have a delta x of t, then delta x dot of t. So, this is a matrix form, you write it vector in case, then you write it this del square v dot del x square of t, then del square v dot del x of t into del x dot of t, then del square v dot del x of t into del x dot of t, del square v dot del dot square of t, this whole matrix, agree. This you evaluate along the trajectory multiplied by delta x of t multiplied by delta x dot of t. Now, see this one, this is the matrix of dimension, if x is a dimension of n variables, then this is the matrix of dimension n cross n, this is n rows n column, this is also n rows n column, n rows n column, and similarly the whole matrix dimension will be twice n into twice n, if you see. Similarly, this one is a n rows n column, this whole thing. So, now in order to this whole thing differentiating with respect to dt, this whole, this is a vector matrix multiplied by column vector, then differentiate with respect to this whole quantity is a scalar quantity, same as this one. Now, in order to that we know that sufficient condition of a second variation of the functional must be, if it is greater than 0, then the functional value along the trajectory what we got it should be a negative, it should be a minimum value of the functional. If it is a delta square v is less than 0, then functional value along the trajectory will be a maximum value of the functional. So, how to decide this one? If you see, it is now in quadratic form. So, our this matrix, compute this matrix whose dimension is twice n by twice n along the trajectory. If this matrix is positive definite matrix, this matrix is positive definite matrix, that indicates that del j square means second variation of the functional will be positive value, means the functional value along the trajectory is minimum. So, our condition is if delta square j is greater than 0 if the matrix delta square v delta x square of t delta square v delta x t and delta x dot of t delta square v delta x of t delta x dot of t. This order may be changed, that delta x dot and delta x, this value will be same. So, it does not matter for this one. We have discussed this thing in details while we have discussed the static optimization problems. So, this x dot square of t compute this matrix along the trajectory, and if it is a, if you want to delta square is greater than 0 implies this must be greater than 0. So, we will check this matrix whose dimension is twice n into twice n, where x is the n variables of the what is called functionals. If this matrix is positive, implies that delta square j is greater than 0. That means, the functional value what we will get, agree, if we put this x star, that means optimal trajectory in the functional values, then we will get it minimum value of the functionals. And if you can write delta square j is less than 0 if the same matrix, that this matrix is less than 0. This implies that the functional value j star of this is maximum value along the trajectory. Similarly, this implies that j star of this is the minimum value along the optimal trajectory. You can write optimal trajectory means x star of t. This is x star of t, you can write it. So, this is the sufficient condition for this one. Okay. So, now let us solve one problems to get how one can solve such type of optimization problem, dynamic optimization problem using the calculus of variation principle. So, example, take an example. So, find, our problem is find the extremal for the functional j is equal to t0 to t0 is equal to 0 to tf, agree, and this functional is given x dot square plus 24 x of t into t dt, agree. So, this functional value j is to optimize extremal, whether minimum or maximum, that we have to find out, and corresponding what is the trajectory for this one. So, where the left end point is fixed, end point is fixed. In other words, x of t0 is equal to 0, agree, at x of t0 is 0 and t0 is equal to 0 here, t0 is 0. That means, you can write it t0 is 0. So, this point is fixed point. You can assign this point as A. This point is fixed point, and the right end point T f is free but xtf value is equal to 2 is fixed. xtf value, whatever the tf value is free, but xtf finally this trajectory should reach at time, whatever the time is there, at 2 units it may reach. So, corresponding to our problem, if we represent that one, it is something like this. So, if you consider x star of t and this is a x star of t near about delta, near about the optimal trajectory, there is another trajectory which you call x star of t. Neighborhood of the optimal trajectory is this. We are calling it a point and this point is B. If you say that that point is T f is free, agree, but x T f, whatever the x T f is fixed, that is 2, x T f is equal to 2, and we have to find out x star of t, the optimal trajectory for this, for the functional for which the j will be extremal, whether minimum or maximum, that for that we have to check the sufficient condition. So, if you just follow our methods what we have discussed, first we have to consider our step solution. So, first you write the v function. V function is what in our case 2 x dot square of t. See, this is our v. V is a function of x t, x dot of t and t. So, the v function is what? Function of v is x to 24 x of t into t, this v. So, write the Euler's equation. If you recollect the Euler's equation, del v del x of t minus differentiation of del v with respect to x dot del x dot of t, partial differentiation of this one, agree, then this equal to 0, and since x is a, in this case dimension is 1. So, this dimension will be 1 cross 1, agree. So, I will just put the value of v and differentiate with respect to x, that is our next problem. So, b is then, if you differentiate with respect to this x, I will get 24 t, first part of this Euler's equation. This is called the Euler's Lagrange equation. Now, second part of this one, you see we have to differentiate with respect to x dot. So, that will be a your 4 x dot of t is equal to 0, then 24 t is equal to 4 x double dot of t is equal to 0. Then your case is x double dot is equal to x double dot of t is equal to 6 t, which equation number 1. This is a simple differential equation. So, I will advise you to recap the solution of differential equation in presence of forcing function, that you recollect this one. Since this is a simple case, one can find out the solution of this one by using what is called double integration. If you do it, first time you integrate, it will get one constant term, second term you integrate, it will get the another constant term, all this. So, you can this, in this case it is very simple. So, I can write the general solution of equation 1, the general solution of 1. What we can write as general solution of this one? X of t is equal to C 1 t plus C 2 plus t cube. For your convenience, just I show you that x double dot of t is equal to 60, integrate both side, x double dot t dt with respect to t t, integrate 6 t dt, then you will get x dot of t is equal to 6 into t square by 2 plus C 1. Then again you integrate this one once again. If you again integrate that x dot of t, again integrate with respect to time t, then 3 integration of t square dt plus C 1 integration of what is called dt. So, if you do this one, that solution is x of t is equal to t square t cube by 3, it is cancelled, 3 cancelled, the t cube we got it. Then you have a this C 1 into t, this one, and another integration constant you will get C 2. So, this is the general solution of that one. Let us call this is equation number 1. So, now let us try, if you differentiate this one once again, then what you will get it there to and see. C 1 into t differentiate 1, this C 2 is constant, this is 0, then 3 t square. Let us call this equation is 3, equation 3. So, now this is the Euler's equation. From Euler's equation we got the what is called trajectory, optimal trajectory of this one, but still it is with us that how to find out C 1 and C 2, that is, and that two constant we can find out from what is called the initial that of a boundary condition, using the boundary conditions. So, let us see that how one can find out that C 1 and C 2 of equation 2. Agree? So, at time t is equal to t 0, that is 0, let us see what is our trajectory t 0 value. So, this is equal to C 1 into t 0, t is equal to t 0 plus C 2 into t 0 cube, t is equal to t 0. Then C t 0 is 0, this is 0, this is also 0. So, C 2 value is 0, the constant C 2 value is 0. Now, initial condition, from the initial condition we got the condition of this. The next is at time t is equal to T f, T f is unknown, is free. Then from equation 2, this is from 2, we can write it x T f is equal to C 1 T f plus C 2 value is 0, we need not to write it here, t cube this. So, C 1 that this value is given to the problem is 2. So, now our C 1 value is what? We can write it, C 1 value is your T f, C 1 value 2 minus 2, take it this side, T f you take it this side, then T f cube divided by T f. So, this is the value of C f, but that depends on the final time T f, because T f is free for us. So, let us call this equation is equation number 4. So, now this is the condition, that means C 1 value we know, C 2 value we know. So, the description of our optimal trajectory is known, provided if T f is known, that at what time of T f that will reach to the our x T f is equal to 2. So, now condition is coming, transversality conditions, transversality conditions. So, so our x T f, if you recollect this, our terminal conditions, that one x T f is fixed, that means delta t x T f is 0. So, this condition will not come into the picture, only this condition will come, Euler's equation, and that this condition will come into the picture, because here x T f is fixed, not free, but T f is free. That here T f free means delta T f is not equal to 0. This implies that this boundary condition must satisfied, that we have explained earlier. So, let us see this one f x t x dot of t minus, and if you recollect this one, see I have not put it star, you can put it star, because whatever the solution you will get it, that is only optimal trajectory star. So, it not necessary put it star, that can, if you get the solution of Euler's Lagrangian equation, you will get the optimal trajectory x star of t, or you can write x of t, this one. So, I am just not writing, if you like you can put it star also there. So, this and del v, the transversality condition when T f is free, but x t x delta x T f is fixed, means delta x T f is 0, then this is equal to x dot of t whole, this I should write it transpose if x is a vector, but it is a scalar. So, not necessary to write transpose for this one. So, this into x dot of t, but do not forget to compute this one as t is equal to T f. You have to put t is equal to T f in the transversality condition. See Euler's equation, transversality is equal to T f. So, do not forget to write t is equal to T f when the T f is free. Agree? So, this. So, now write this equation, that delta x is a v of x is equal to x dot square of t plus 24 x of t into t. Now, this you differentiate with respect to x dot, that means this is the v, we have differentiate with respect to x dot, means this is a 4 x dot bracket 4 x dot of t into that other term is 0, because I am differentiating with respect to x dot. So, it is a x dot of t is equal to put t is equal to T f is equal to 0. Now, see this one, that is a 4. So, there is a 2, you divide by this into 2, then it will be x dot t is equal to T f. I am now putting the t values, t is equal to T f plus 12 x T f into T f minus 2 x dot t is equal to T f square, this is square, I missed it. So, this is equal to 0. So, finally, therefore, x dot square T f is equal to 12 x dot T f is equal to 12 x T f into T f. I am correct. So, this is I am writing x 2 x dot square 24 x T f. So, 24 T f. So, 4 that is your x dot 4 x dot t into x dot. So, it is a twice of this one. Okay. So, if you take it this that side left hand side. So, it is a minus of this equal to 0. Okay. So, this is minus. So, now I know this value of what is called T f x value, x solution of this is here, solution of x dot, you see solution of x dot I know that C 1 C 1 x dot is x dot t is C 1 3 t square, as t is equal to T f, as t is equal to T f, x dot T f C 1 3 T f square. So, I will write x dot value is C 1 plus 3 T f square whole square, okay, minus 12. So, x T f value is what? Say x T f value is 2, okay, x T f value is given 2. So, this is 12 into 2 into T f is equal to 0. So, if you simplify that one, C 1 square 9 T f 4 plus 6 C 1 T f minus 24 T f is equal to 0. So, what we get C 1 square 9 T f 4 plus 6 C 1 T f 6 C 1 T f square here T f square, then 24 T f, we got it, this is equal to 0. So, now C 1 expression already we have derived the C 1 expression, if you see in terms of T f. So, I will put the value of C 1 expression 2 minus T f cube by T f in this expression. So, if you put this, it is in this expression, then what we will get it, just see this one, I am just putting this in this expression. So, C 1 is what 2 T f cube by T f whole square, this is C 1, this value is C 1, this value is C 1 plus 9 T f 4 plus 6 C 1 is what 2 minus T f cube, 2 minus T f cube divided by T f into T f square minus 24 T f as it is, minus 21 T f as it is, agree, T f. Look in that, if you see this one, this is the equation of this one. I am just putting the value of C 1 and where C 1 is 2 minus T f cube by T f. This value C 1 I am putting in this expression and then I got it. So, if you simplify this one, if you simplify that one, finally, we will get the expression. So, I am skipping few steps for the, there is a just is some academic exercise you have to do it to arrive in this expression. So, T x this T f 6 4 T f cube plus 1 is equal to 0. So, now this is the equation which one can solve for T f. Let Z is equal to T f cube. Okay. Now, if it is this one, I can write it that this T f expression, that Z square minus 4 Z plus 1 is equal to 0. So, Z is equal to, it has a 2 roots quadratic form. In fact, it is a, you will get it, how many roots is here, for the time being Z I am getting it minus b means 4 plus minus root over b square means 16 minus 4 a c divided by twice a. So, that will be 2 plus minus, that is root 3. So, it is a 12, 2 is taken out, then this. So, that Z has a roots of Z 1 has a root of 2 plus root 3 1, which value is 3.732, another is Z 2 is equal to 2 minus root 3 and that value will be 0.2679 and ultimately I have to get it Z T f. How T f is related? Z 1 is related T f 1 cube. So, our T f 1 from Z 1, if you see Z 1 is equal to T f cube, T f 1 cube is equal to what we got it, that is 3.732. So, T f 1 is equal to 1.551, this one, and Z2, another case is Z2 is equal to T f2 cube, which is equal to 0.2679. So, T f2 is values is your 0.6446. So, there are two final time is there, 1.5 times the state will reach XTF is equal to 2, another time is 0.6446, the our final state will reach to 2 units. Agree? So, once I know the T, I can find out the C1 for T is equal to, note C1 is equal to 2 minus T f cube by T f, and for T is equal to, for T f is equal to T f 1, that is your 0.15 second, 151 second C 1 value, you will get it 2 minus T f 1 cube divided by T f, this is T f 1, okay, T f 1. So, that value will come minus 1.117, this. For another case, for T f is equal to, or you can say what is our trajectory, x t of this is equal to C 1 t plus t cube, and I know C 1 value, one case is minus 1.117 t plus t cube. So, this is the optimal trajectory for this one, when at time t is equal to 1.551 second, this x t f 1 will reach the state is variable is 2 units. This is one solution, and if you plot it, let us call, you are advised to plot this x t versus that time, agree, and that trajectory at time, that trajectory let us call is some name you give it, curve 1, that trajectory is called curve 1, curve 1. Now, next situation, that is what we will see, that is for T f is equal to, our time is that for T f is equal to T f 2, that is our time is what, if you see the T f is equal to T f 2, that is what we have got it, that 0.6446 second, agree. Then C 1, this implies C 1 is equal to twice minus T f 2 cube divided by T f 2. So, this value will come 2.6871 constant. So, corresponding trajectory, optimal trajectory, that x t is equal to C 1 t plus t cube. So, it is C 1 is 2.6871 t plus t cube, agree. So, you are once again you are advised to plot t versus time and call this curve, that this optimal trajectory curve is curve 2. You can easily plot it, this t versus t is 0 to, you know how long you have to plot it, this is valid for t is equal to T f, that value is your 0.6446 second, you plot it up to this, t is equal to 0 to this, and that one you plot earlier one, t is equal to, you have to plot this plot, you do it, t is equal to T f 1, which is 1.1551 second, agree. So, there are two trajectories are there, which will give you the optimal value or extremal value of the function. Both are what is called optimal trajectory. One case you justify your thing, one case will give you the maximum value of the functional, other case you will give it will give you the minimum value of the functional. Out of these two trajectories, one will give you the maximum value of the functional, other will give you the minimum value of the functional. Both the trajectory reaches is final value at x t f is equal to unit is 2 units, but different times this one. So, I just advise you make your comments on the curve 1 and 2, which I asked you to plot it and make your comments, which one is giving the optimum in the sense maximum value of the functional, which trajectory will give you the minimum value of the functional values. So, the whether minimum or maximum value function will give you, you can find out how that our sufficient condition you use it. What is the sufficient condition? If you recollect this one, that our matrix, that Hessian matrix, if you recollect in static optimization problem, we have discussed as a Hessian matrix. The Hessian matrix is del v dot del x square of t del square v dot del x of t into del x dot of t del square v dot del x of t into del x dot of t del square v dot del square del x dot square of t. This value you find out the trajectory x is equal to x t is equal to x star of t. What is x star of t? One case we got it x star of t. If you see first case when t f is equal to 1.5 second, we got it minus 1.117 t plus t cube when t f is equal to t f 1 is equal to 1.15 second. So, you put these values, because in this expression you differentiate with respect to x gradient v gradient you find out with respect to x, then again once again differentiate, and whenever you got it x, you put these values of that x is equal to t f. Again, then you x is equal to t f you put it and find out the what is the that whether it is a positive definite matrix or not. If it is a positive definite matrix, if this is positive definite matrix, then functional j star is minimum value will get. If this is less than 0, then j star is will give you the maximum value of the functional. So, this way you can check it. So, this we have shown it how to solve a problem, dynamic optimization problem by using the calculus of variation concept. So, now we will see slowly we will go to application of what is called calculus of variation to a control problems. The control problems means you have a dynamic system, any system one can model into a mathematical model, either transfer function model or state space model or different model. Our problem is concentrated to describe the dynamic system in terms of differential equation. In terms of differential equation, let us call if the dynamic system is described by nth order differential equation, one can convert by selecting the suitable variables into convert the differential equation, which is order of n can be converted into a n first order differential equations. So, that is called is a state space representation of a dynamic systems. whether the dynamic system may be linear or nonlinear, but we can apply the what is called the calculus of variation principle to find out the optimum value of the functional or objective function optimum value. Let us see how to do this that one. So, now application of, you can say the application of calculus of variation approach to optimal control problem solution. So, that is our problem. Let us consider our system or plant. Consider the system, the dynamic system or plant is described by x dot, capital X I am now using to represent if the variables are more than 1, then I am represent with a capital X. So, let us call that variable is n cross small n cross 1, n variables are there. So, that is a function of x t, u t and function of time. So, this function also we have a n function there okay, is a vector. So, let us call this is equation number 1, and if you see that vector dimension is n cross 1, and we assume that we have a m inputs are there to the system. So, and this is the time. So, this is a description of what is called our dynamic system in terms of variables, and how many variables are there? N variables. How many inputs are there? M inputs. So, our problem is that you find and corresponding performance index or objective function, corresponding performance index or objective function is j is equal to s function of x t of t, and that x t is equal to T f x t f, or you can write it here better, you write t is equal to T f. The terminal time, this function below, this is a scalar quant, because objective function is a scalar quant, this is also scalar quant, scalar one. It can be a quadratic form, agree, but it is a scalar, it is a function of x t and t. And then we have a functional T 0 to T f v is a function of x t, is a function of u t, and t, let us call it d t. Agree? This is the function of that one. So, and this we call this term, first term is called terminal cost, and this s is a function of x of t and t. It is differentiable with respect to time and t, that is one, and that function is a continuous function, and this term is called the cost integral cost function. And that j is your performance index. So, our objective is, if you see, our objective is to find a control signal in the system. Suppose we have a system is there, that system, and we apply the input u of t, and the output is, let us call the states are the output. So, we are accessing the states. Our problem is to find a control input u of t such that this performance index, what is the performance index? That performance index is indicating that indicating 0 to T f, and it is a function of x t, u t and t. U t is the control input. Once the control input is that regulates the state x of t. Agree? So, this plus the terminal means as time t is equal to T f, what is this function value, that is called the terminal cost. So, that means we want to drive the state at final state at particular point, agree, and that represents in terms of a quadratic form. Agree? We cannot write the x T f only, it is quadratic, but that quantity must be a positive quantity or 0. So, our problem is find a control input which will control the state of the system x t such that this performance index is minimized. Not only that control input and state, because control input state will satisfy this equation. That means, this you find out the control input u in such a way this functional is minimized or maximized, control input control problem is minimized, let us call, and then subject to this constraint, and that constraint is the equality constraint. So, our problem is now becoming a what is called a constraint optimization problems, and that constraint is equality constraints are there. So, I just write the statement of the problem. Objective: find u of t whose dimension is m cross 1, number of inputs is m, that means control law. Only that minimizes performance index. P I means performance index. Let us call, we just write this equation is equation number 2. Agree? That performance index 2 subject to plant dynamics, subject to equation 1, plant dynamics, system dynamics, subject to this such that no. Okay. Our problem is find u to only that minimize the performance index subject to the constraint, 1. That means, whatever the control input we generate and x generate, this must satisfy the equation number 1. That is such an this type of problem is called such an problem optimal control problem is known as Bolja problem. So, this is our problem. Now, let us see, if you look at these things, what is difference from the earlier problem? We have a same thing here. Earlier problem also we have to what is called integrand v is there, we have to integrate 0 to T f, and that functional we have to minimize. But in addition to that, there is another term is there, which will call what is called is the terminal cost, and that can physically represent the final state of the system, agree, and in terms of it quadratic form this, and that quantity is must be a positive one, that one. So, this not only this, there is another constant is there, it must satisfy this equality constant, and this equality constant is nothing but a what is called that dynamic equation of the system. This equation is the dynamic equation of the systems. So, by some means if you can push it this term into the integrand part of this equation, then our problem is similar to the earlier problems. Let us see this how one can do this one. So, note, because our job is how to push this term into a integrand part of this functional. Okay. So, now see this one, we can write it now T 0 to T f ds x t, which is a function of time, and dt. We have just mentioned earlier that this is the continuous function which is differentiable with respect to x t as also t. So, this I can write it this into dt is nothing but a, that if you see this one, this nothing but a x of t comma t is equal to T f minus x, you can write it x t of t is equal to T 0, which is nothing but a x T f minus x T 0 and T 0. Okay. So, in place of this one I can write this term and this term. So, this limit is an integrand limit of this one is same T 0 to T f. So, I can push it in equation number 2. So, if you push it, let us call this is equation number 3. Agree? Using 3 in equation 2, using 3 in equation 2, what we get it? Just look at this expression, that this is this minus this one, I am using this one. So, if you do this one, j of dot is equal to integration, I am just skipping one step, this v of x of t u of t, then t dt, that one plus T 0 to T f ds x of t dt whole bracket dt plus s of x T 0 and T 0 this, and this is the constant term, because you know that t is equal to T 0, what is the initial condition of this one, you know this one, this is the constant term. Now, our whole problem is now leak. If you see, our problem is now this one, minimize this one, in place of minimizing this one, minimize this term, let us call equation 4. Agree? This is equation number 2, 3 and this is 4. Minimize equation 4 is same as minimize equation number 2. Agree? Minimize equation number 4 such that minimize in the you find out optimal value of control u such that this is minimized and as well as this equation is satisfied. Since this is a constant term, that optimal trajectory will remain same if you consider the minimization of this part only. So, instead of whole thing minimization, this part minimization, whatever the optimal trajectory you will get it, agree, for u transpose and x transpose, that will minimize that as well as it will satisfy this one. So, we will stop it here. Next class we will continue this lecture in detail.